Hey guys, welcome back. So I'm going to go ahead and move this over here and we will move on to our next section now that we're done with our intro. And what are we going to be talking about now? Well, we're going to talk about aqueous solutions. So we've got a couple of definitions that we need to go through, some vocabulary that we need. So an aqueous solution is defined as a homogeneous mixture of two or more substances. Homogeneous, meaning it's uniform in nature or character throughout. Think about vanilla ice cream. It's very easy for us to look at that and think that it's one thing. I mean, we know that it's not exactly the same throughout. We can see visually that there are parts of it that have speckles in it, and so it's not really the same, but it's actually, I mean, it looks on first glance like it's all the same thing. However, if we look at a different kind of ice cream, like Rocky Road ice cream, then it's very easy for us to see that that's not the same. And that's a heterogeneous mixture where areas are different in nature or character. It's very easy for us to see that. Something like Rocky Road is very easy to see that because they're actually separate particles that we can see within it. You know, there's the marshmallow and you know, the, I can't remember what all is in it, but there are very definitely different particles within it. So it's easy for us to see that. We also talk about some different parts of that mixture. So one of them is called the solvent, and it's the stuff that's usually the liquid that everything is dissolved in. It's a substance present in the larger amount. Okay. We also talk about the solute, which is the substance that's present in the smaller amount that's dissolved in it. Okay. So when we talk about salt water, the water is the solvent and the salt is the solute. So it's what's dissolved in the water. An aqueous solution is a solute initially that is dissolved in water as the solvent. Okay. So an aqueous solution is something that's dissolved in water. So water is our solvent. Not all solutions are aqueous in nature. Okay. Not always are we dissolving things in water. Sometimes we dissolve them in other stuff. Okay? We used to make mixtures, especially at home when we were mixing like um, stuff in the garage. We would make different mixtures of things, especially cleaners, and we would mix different things to see if we could get stuff to dissolve, especially like paint thinner, things like that, which we can't actually sell anymore. But that was, you know, a prime example of dissolving things in other stuff to see if we could get them to come away. All right, but that is the kind of thing that we're talking about is what else can we dissolve them in? Okay, so it's not always solvent that we're using as water that we're using as a solvent. Okay. Now, one of the other terms that we use, that we often use, is electrolytes. And you've probably heard this term before. What we always talk about electrolytes when we talk about Gatorade. Gatorade is a very well commercially known product. It was developed at the University. Yeah, it should be University of Florida, and it was meant to make their athletes perform better. So what they did was they dissolved a bunch of salts in water to help their athletes. Now, when we say salts, what we mean by that is any ionic compound. And so what happens when those ionic compounds go into solution, they break up. And so they become cations and anions again. Okay. So anything that has that capability to become cations and anions again is known as a salt. Okay. That's what we mean by salts. So lots of things have these salt properties and they can be dissolved when we put them in water. Now, not everything does this. Lots of things don't. So if they're not ionic compounds, they typically don't dissolve. So even some things that look like they're compounds don't do this. HF, even though it is actually an ionic compound, does not come apart. It has a very high affinity between that hydrogen and that fluorine, and it doesn't come apart. Okay, so things can be strong electrolytes and they come completely apart, or they're weak electrolytes, they only kind of come apart, if at all. Some things are non-electrolytes and they do not come apart. Okay, so these things do not come apart. And so we can talk about them being strong electrolytes or weak electrolytes or non-electrolytes. Okay, and those terms apply to how much they come apart. In 111, we spend a lot of time talking about how much they come apart. Okay, and it has to do with what kind of ionization they have, whether they're really ionic compounds or not, and how easy it is to get them to ionize. Okay, now if they're good electrolytes, then that means they are good conductors, so they can carry electrical charge from point A to point B. So if they can carry good electrical charge, it is not a good idea to be in water with them if there is electricity around. Okay, so that's not always a good idea. So there are things that we have to be careful with when we do that, right? So we need to be careful when we're dealing with some of these components. Okay, so strong electrolytes, weak electrolytes, non-electrolytes, and you may see some questions about whether they're strong electrolytes, weak electrolytes, non-electrolytes. You will see there are some tables in your exam handouts where we talk about some of these things. Let me pull those. Where are they? So places where I talk about this. Strong acids, strong bases. Obviously, there are other reasons that we talk about whether they're strong acids or strong bases, but this is one of the places where we talk about whether they're strong or weak electrolytes. Okay, so if they're in the strong list, then they completely ionize. Right, so that's one thing. Solubility rules. When we talk about whether they're soluble or not, if they're soluble, they completely ionize, they completely come apart. Okay, so this is one of the places where we talk about that. If they are insoluble, they do not completely come apart, and therefore they are not good things to talk about when we talk about solubility. They're not very readily soluble. It is a different way of looking at that same information. We'll talk about this in a bit. Okay, other places that we will see this. This is a measure of how soluble they are. So high solubility products constants mean that they are very soluble. Low, small numbers here mean that they are not soluble. Ionization constants of weak bases, weak acids, mean that these things do not come apart well. Okay, so that is something that you should be aware of. Okay, and I wouldn't worry about these at all. So that's not for you, but those are things that we can talk about. So those are hints to you as to whether they come apart well or not. And those are terms that we use when we talk about those. Okay. So those are our electrolytes and what we mean by those terms and what are some of the consequences of those things. Now, when we talk about water and we talk about electrolytes, understand that water's great. It's an awesome, awesome compound, but it has some really unique properties. The fact that water has some really unique properties means that it does some funky things. And it's one of the reasons that life exists on Earth the way that it does. That's why all of this stuff that happens here happens. The fact that water exists in the shape that it does with the charge separation that it has is part of the reason that life exists. It has what we call a partial dipole. So there is a net negative end on this molecule and a net positive end on this molecule. So there is a charge separation, a permanent one, where we have negative parts of this molecule and positive parts of this molecule. It's not a real charge separation because it's not a full separation of charge. Okay. And of course, the fact that it happens sort of at this end and sort of at this end, and then we've got some squishing of the angles because of that. So it's a partial charge and a dipole moment because of it means that we have some interesting properties. So water is neutral, but it contains a negative end and a positive end. Because of the separation of the charge, it interacts with other charges. So if I put something into solution that can come apart, like a sodium hydroxide, which is made of NaOH, that NaOH can become an Na plus and an OH minus. And that Na likes to come hang out over here by the negative end, and the OH minus is to come hang out over here by the positive end, right? And so that interaction is favored because of this partial charge. So this ability of this positive end and this negative end to hang out by those charges gives it the ability to do that. And what that means is that even though there's a positive and a negative here, it's actually more favorable for those two things to come apart and interact with the water molecules, because there's so many more water molecules than it would be for them to stay together and just hang out with each other, because there's so many more water molecules. And so we can get this cage of water molecules around each of those ions that is more energetically favorable than what it would have if it was just hanging out next to that other ion. So that's why they do what they do. And so that hydration that happens, where it becomes surrounded by that cage of water, is because of that stability that it gets from coming apart. Okay. So that's one of the wonderful things that we get from that structure for the water. Okay. So that's part of why we talk about, what happens when we go into solution. Okay. We get a lot of fun things because of that structure. All right. Now, acids, bases, and strong versus weak electrolytes. Now, when we talk about strong electrolytes, strong acids completely dissociate. This process is called ionization. So HCl, which is one of the most common things for us to talk about, completely comes apart. We draw this arrow. This arrow is in one direction only. It only goes this direction. So HCl goes into water and it becomes H plus and Cl minus. We never write this as a two-headed arrow where the H plus and the Cl minus come back to be HCl. That does not happen. It always goes into water and becomes H plus and Cl minus. That's it. It's said to be a complete separation of the cation from the anion. That single-headed arrow indicates the reaction only occurs in one direction. Okay. Is it important that you understand that? Not really at this point, but you will see that, and you will see that it only occurs that way. And I will kind of flip out about it, because it's important that you understand that it only goes that direction. It always comes apart, and that means that we know things about it. So if I know what the concentration of this thing that I put in here is, that means that I know what the concentration of this is and that is. That's important. Okay. Now, if we come over here and we talk about something that's a weak electrolyte, this weak acid right here, acetic acid, CH3COOH, does not completely dissociate. So it comes apart, but I don't really know how much it comes apart. Now, I have ways of knowing that because I know certain things about it. But without doing a lot of math, I can't tell you how much it's come apart. And that's dependent on a lot of things, like the temperature and the pressure and a whole bunch of other stuff. And it's complicated. Okay? It's very complicated. And so I can't tell you, based on what the concentration was that I put in here, like what I measured out, exactly what this concentration is and what this concentration is. So it's not easy like this one. So I can't say with 100% certainty what this is and what this is. And so it's not simple. And so that kind of chaps my hide, because it's a lot more work to be able to figure out, well, what exactly are we talking about? And that's because this thing will come apart, but it will go back together. And there are things that can make more of it come apart or more of it go back together, depending on what exactly is going on, or what the temperature is, or what's happened in that solution, or what else is in the room, or any number of things can move that. And so because of that, we have to have this dual-headed arrow that indicates that it could be moving either way. And there are other things that can happen. And it's a more complicated situation where we have to think about all of these other things that could be happening. I don't like that. I like situations that are much more simple. And so it's always prettier and nicer and cleaner over on this side of the page where I know exactly what's going on over here. You know, it's so much cleaner over here. Now, can I do this? Can I handle this? Can I get to a place where I know exactly what's happening? Yeah, I can, but it's a lot more work. So I like to hang out over here where I know exactly what's going on. Okay. So our weak electrolytes are not completely ionized. We have a situation where things are going on, they're more complicated. We have things we have to consider. There's a lot more happening. And because there's things going on in both directions, we have a system that's called equilibrium. Okay. If you want to think about equilibrium, you're already aware of systems that are in equilibrium. You are. Think about a store. When a store opens, once it's been open for a couple of minutes, there are people going into that store, there are people coming out of that store. There is never a situation where there's only traffic in one direction. That happens when you open the store, and it happens when you close the store. But it does not happen at any other time where it's only one way, unless an emergency is happening, and that's a slightly different issue. Okay? So there's more going on. We never really know at any given time how many people are in there or out of there or what exactly is going on. It's more complicated. And so that's an equilibrium situation. It may appear that nothing is happening. It may appear that there are always, 25 people or 50 people or whatever inside of it. But there's always people coming and going. And so that's an equilibrium situation. It may not appear to be changing, but it is changing. And so that's, like I said, more complicated. All right. So that's a different situation, and we do call that equilibrium. Okay. Questions, comments, problems on any of the terminology that we've covered thus far? Okay. Now, what else have we got? Oh boy. Now let's talk about our two types of reactions that we intend to be talking about here. And I'm going to take a break for just a second. I have to do something. I'll be right back. Okay, guys, thanks for that. So precipitation reactions are one of the most fundamental reactions that we talk about. So when we talked about reactions initially, I said a lot of them are replacement reactions, do-si-do reactions, where we trade partners. That's something that we call, another term for that is a metathesis reaction, aka double displacement. So we've traded partners. And a precipitation reaction is a specific type of that. And what happens is that when we do this specific type of double displacement, one of those products is no longer soluble. So we've taken and we've mixed these two things together, and one of those products says, oh, uh-oh, sorry, I don't like being in solution. So for whatever reason, those two things come together and they don't want to be in solution anymore. They no longer want to be aqueous. Their attraction for each other is higher than the attraction for those ions to the water. So we'll talk about some of the ways that we know how that's true. Those are our solubility rules. But what we do when we look at this is we look at that reaction, we look at the two products that would be formed, and then we see if either one of them is going to be insoluble. That's what we talk about. Okay. So this process helps us to learn how to write those reactions, balance those reactions, look at what are our potential products, predict if they're both soluble, and then we can write a couple of different types of reactions that go with those. And we'll talk about what those types of reactions are. In my opinion, this is a really good way to understand the fundamentals of the reactions that we're talking about. Okay. And to understand solubility and dissociation and some of the terms that we've been talking about. All right. So Sorry, a little bit of lag today. Now, how do we know if an insoluble product is reformed? That depends on the solubility of the products. So, solubility is the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. Temperature affects solubility. And you probably know this. Now, if you're an industrious person like me, you probably played in the kitchen a lot as a kid. I did. I absolutely did. My mother was absolutely nuts and she loved to do stuff in the kitchen. And she wanted me to get in the kitchen and get messy and do all kinds of things. And she encouraged me to do that pretty much anywhere and to watch lots of other people do it and to get involved in doing it. If you've never had the pleasure of doing some of these things, I highly encourage you to go play in your kitchen. It's so much fun. And if you've never made rock candy, it is one of the most entertaining things that you can do. And there is this website that I've linked here that talks about how you can make your own rock candy in the kitchen. And all you gotta do is take some sugar, put it in water, heat it up, you can put some color in it, and then you can crash out the sugar on a piece of stick, like a stick. Go to the store, buy some sticks, stick it in there, and then boom, you make these lovely things. Now the first time you make them, they're not gonna look pretty. I understand that, but you get to have some fun. If you've got kids, you can play with your kids. You get to be really good at it after you've done it a couple of times, and it's an awesome process. You get to watch the crystals form. You get to learn what makes good crystals and what doesn't. You get to learn, like, what colors make better looking crystals, because there are some that look better than others, stuff like that. And sort of what are the conditions that make better looking crystals. Like, if you heat it up and you're really careful about how you handle it before you crush them out, they look better. If you're not so careful about how you do it, then they kind of look like crap. If you've ever had one of those, like, uh, they have like grow kits for salts too. Those are really fun. And you learn some of the same lessons in growing those things, and you know, I think those things are fascinating because you get to learn about how do these salts form and what are the keys to growing those salts, and you learn a lot about crystal structures in doing it. Is it necessary? No, absolutely it's not. Is it important? I don't even know that it's important, but I thought it was fascinating. So, whatever. It was worth a little extra money to me to go play with such stuff. But solubility is definitely based in that because you can raise that temperature and then go in and let it cool and then crash that out and see that effect. As you lower that temperature, you can get it to crash out. See that you get these things. If you can't get it to happen, you can go and buy them from somebody else who's done them, who's mastered the art of making it happen. So this is how that process works. Okay, so this is an effect of solubility. All right. So sugar is only so soluble unless you raise the temperature. Once you've raised that temperature, then you can lower that temperature and get it to come back out. Okay? So that's an effect of solubility. Now, most things are more soluble as we raise the temperature. But for most people, if you've been in the kitchen, you know that that's not always the case. Any of us who have ever made gravy know that that's not always the case. So some of our thickening agents are more soluble at low temperatures than they are at high temperatures. And so as we raise that temperature, we can get things to thicken. Okay. Why is my brain failing? I'm old. My brain fails on a regular basis. And I can't think. Anyway, sorry. On here. Nope, can't find it. Anyway, so our thickening agents is one of the distinct things that doesn't do that. And we have sets of rules that will determine what is soluble and what is not. These are our solubility rules. Okay. So these are the rules that we can apply. These are rules that we have to apply in order. So if I find the rule, find it in the rule on the top, then I don't go any further to look for it. Okay? And what it says is all common compounds of group 1, 1A metal cations, so lithium, sodium, potassium, those guys are soluble. So if I have something and I'm considering it, it's attached to lithium. I don't care what its anion is. If it's a fluoride, if it's a bromide, if it's an oxygen, it doesn't matter. It's going to be soluble. Okay, that's it. If it's a common compound of ammonia, it's going to be soluble. Doesn't matter what it's attached to. Okay, it's going to be soluble. If it's attached to nitrate, NO3 minus, it's going to be soluble. If it's attached to CH3COO minus, it's going to be soluble. If it's attached to ClO3 minus, it's going to be soluble. If it's attached to perchlorate, ClO4 minus, it's going to be soluble. If it's attached to bromine, unless it's attached to silver, mercury 1, Hg2 2 plus, or lead 2, Pb2 plus, then it's soluble. So if it's AgBr, that's not soluble. If it's Ag or Hg2Br2, that's not soluble. If it's Pb or PbBr2, that's not soluble. That's what those say. Okay. And so you've got to look through that list that way. Now, if that doesn't work for you, if this list does not work for you, and I can guarantee that these always work. Okay. These rules as written will always work. But there are some things that it's hard to work with those for. I can understand. So there is another form that is on here, which is actually what you'll find in Alex. And this is the solubility chart that you'll find in Alex. Okay. So this is the list that I gave you on that slide. This is exactly the same list. Here are some of the water insoluble components and their exceptions. So you'll see like CO3 2 minus is almost always insoluble unless it's attached to a group 1A cation or NH4 plus, which is from here. So again, this applies unless it's, so it always applies. So that's what we're talking about, okay? But there is this chart. Now, you can look at this chart. Not everything is in here. Not everything is in here. And you'll find that some of these things aren't in here. So Na plus is usually in here. K plus is normally in here. But not everything is. And if it's not in here, it's usually because it's one of these things that it says it's always one or that kind of thing. So if it's not in here, it's probably one of those, and you just need to refer to that. Okay. There are some weird things that are in here, like O2 minus. Sometimes you just get no. Sometimes you get reaction. So you've got to be careful with those. There are reactions that happen with those. So we've got to be cautious with that. Okay. If it says slight, that means that it is slightly soluble, yes. But that does mean that you will get some solid and not all of it will be soluble. Okay. So that is what that means. If it says reaction, that does not mean that it is soluble or insoluble. It means that something actually happens when you do that reaction. You get a product out of it. So that is not a solubility issue. So those are the things that we talk about when we talk about these solubilities. So don't give me, well, it wasn't in the chart, or it didn't appear here. And if it didn't appear here, then there is something in here that should have told you what it was. Okay, that's all there is to it. There is something that will tell you. Now, there are a couple of weird things on Alex where you're not going to find something about it, and it's really weird, and I don't understand that, because if they're going to put it on Alex, then it should come out of here. But if it's an Alex thing, then that's that. Okay. If it's one of mine, you should be able to find it in either one of these. Okay. There should not be an exception to. Okay. So those are the solubility rules that we talk about when we talk about whether or not it's soluble. Okay. So these are the rules that I'm expecting you to use to determine the solubility of these materials. So they are available on the test. You are expected to use them. So you need to know how to use them. So I want you to practice. And I'm going to pick 3 of these out of here. And I'm going to walk through them right now. And then I'm going to expect you to go and look at them. And I'll tell you what the answers are. Okay. I'm going to pick 3 out of this. And I'm just going to randomly pick 3 of them. I'm going to start with this one right here. This one right here. And that one right there. So BaNO3. I'm going to pull this over here and then I'm going to pull up my handouts. So BaNO3. So I start up here. BaNO3. NO3 is right here. It says all common compounds of nitrate are soluble. So this is soluble. Rule 3. CaClO3. 1, 2, 3, 4, 5. Soluble. Rule 3. No, that's not 3. 1, 2, 3, 4, 5. Sorry. Rule 5. I can't count. No. And then Mg3PO42. All right. Mg, no PO4. Okay. Compounds of phosphate. Phosphates of group 1 and NH4 are soluble. All other ones, it says, are insoluble. So insoluble 1, 2, 3, 4, 5. Insoluble 5. And it's insoluble rule 5 because I did not find it in a group 1 metal. So Mg is not a group 1 metal, so therefore it is not soluble. Okay? So that's what I've got for those. All right? Questions, comments, problems on what I did. I'm going to take a break here. I expect you to do the rest, and we will come back with some answers. All right? So I'm going to come back with the answers put up for the rest of it. Okay, I'll see you soon. Okay, guys. So I said I was going to come back with some answers. And what I've done is I've written down whether it was soluble or insoluble and the rule that it was based on. So this first one, Na2CO3, is soluble based on rule 1, and it's because it's an Na+. Second one, soluble, rule 1, based on K+. NH4OH is soluble based on rule 2, because it's an NH4+. This one, AgC2H3O2, is soluble based on rule 4. Now, even though this says CH3COO-, C2H3O2 is the same as CH3COO-. It's just written a different way. CaOH2 is soluble. It's based on insoluble rule number 4. So 1, 2, 3, 4. Compounds of OH-. It says hydroxides of group 1A cations, NH4 plus, Ba2 plus, Ca2 and Sr2 plus. So soluble exceptions of OH- are Ca2 and so it's one of those exceptions to that rule. The next one down, Li2S. Solubility rule 1 is all of the Li's. It's also insoluble down here, the compounds of sulfide, S2-. It says soluble exceptions. Sulfides of group 1A are soluble exceptions. This last one, NH4CO3, solubility rule 2. All common compounds of the ammonium ion are soluble. So, and of course, if you look at this one, the compounds of carbonate ion, the soluble exceptions include NH4. So those are my rules that I have used to state whether they are soluble or insoluble. Questions, comments, problems on those? All right. So that is the expectation, is that you can pick these things apart and find whether they're soluble or insoluble based on these rules. Okay? If you want to use the charts, you're perfectly willing to do that. You're welcome to do so as well. You should be able to use these charts just the same way. Okay? Okay. Moving on. Questions, comments, problem. I'm going to take a pause here. I'm going to come back into this in a little bit and start the next part of this video. I want to get this broken up so I can get it loaded. So, see you guys soon. Thanks.